So now back to strategies for counting. And I want to go over a couple more specific things today, but I want to start by giving some general tips for counting. Sanders' top tips for counting. So the number one thing is to rely on the fundamental rules that we have taught. Namely, the rules for product, sum, subtraction, and division. This thing is AKA inclusion, exclusion. Because you will remember, even last time, when we defined permutations and combinations, we basically defined them using these rules. So the fundamental rules should basically get you everywhere you need to go. Except I will make one comment in the next section about one more tip that I think is very good to have on hand. But, okay, so in addition to these, there are a few categories of problems that it is good to have in mind to guide you. So, relevant to what we've been talking about last time, your counting problem might involve order or no order. So ordered or unordered. Also, it might involve repeats or no repeats. And what I'm going to introduce today is things that are related, but not quite the same or different as these two things. But there's this way that you can model a lot of counting problems as putting balls in boxes. So I'll give examples of what that means, but for now I want to say that the main things you care about for these problems are distinguishable, or indistinguishable balls, and distinguishable or indistinguishable boxes. So this is when you're thinking of it as balls in boxes type problem. And basically, there are lots of different combinations of these factors, and each combination sort of has its own rules and techniques. So they don't all look like each other. And again, my solution for this is to tell you to try to think about things in terms of the fundamental rules and rely on that, instead of trying to memorize a bunch of different cases. But if you want to know more about this, you can look up the 12-fold way. And that should lead you to some discussions of how you can have a sort of clear accounting of kind of what all the cases are. But again, there's a lot of them and they're all quite different. So I will recommend to rely on the fundamentals. So let's start doing some examples with these things in mind. Example 1. How many ways excuse me, how many ways are there to reorder the letters in the word Mississippi? So basically, how many ways are there to rearrange this set of letters? And we have seen things a little bit like this before. We did an example with ones and zeros at the end of last lecture. And the point is that this is a case where order matters a little bit, but not entirely, because, for example, we have 4 S's, and we don't care about rearranging those because they're all identical. So, I'm encouraging you to think about things in terms of these fundamental rules. So here is how you might do that. So we're going to use the division rule because it's inconvenient that these letters are identical, so we're going to ignore that for a moment. So if we consider all the letters to be distinct, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Jesus. 8, 9, 10, 11. 11 letters in the word Mississippi. So that's 11 factorial orderings. Okay. But we have overcounted because, like we said, we don't care about the order of the letters that are identical. So we have 4 identical S's. So we should divide by all the ways to reorder those 4 letters within themselves. So that's dividing by 4 factorial, because there are 4 factorial ways to order those. And similarly, we have 4 identical S's, 4 identical I's, that's another divided by 4 factorial, and 2 identical P's, that's another 4 factorial, that's the 2 factorial. So the total is 11 factorial divided by 4 factorial, 4 factorial, 2 factorial. And if you want to include the little m, if he's feeling left out, you can include 1 factorial. That won't change anything, but it will make it maybe more clear how each part plays a role. Let me erase that for now. So that is one way you can approach this problem. But I do want to give you another framework, if it is more helpful to you. And sometimes I think it probably will be. So here is the balls in boxes interpretation. So maybe let me give a little introduction to this. As you can probably tell from the name, what balls in boxes problems are about is how many ways can you put some balls in some boxes with, whatever conditions or restrictions you would like. And as with some of the counting problems that we've seen, it helps if you can be a little bit flexible about what you consider to be balls and what you consider to be boxes. So in this case, and again, I think this should remind you of the ones and zeros we did yesterday. The balls are letter positions, and the boxes are the letters M, I, S, and P. So just to give a quick explanation of this, for example, letter positions 1, 2, up to 11. So ball 1 going in box P means our word, our reordering starts with a P. So let me write that. Ball 1 in box P. So it may not be immediately natural to think of the positions in your word as being balls that you put in boxes. But if you start thinking about things this way, you will get used to it, and it will start to become familiar. So the problem becomes, how many ways to place 11 distinguishable balls in 4 distinguishable boxes? So that we get 1 ball in box M, 2 in box P, 4 in I, and 4 in S. All right, let me rewrite that. That's a little bit lame. 4 in box I, 4 in box S. Better? So the general rule that we can interpret from our counting up here, here's a general rule. So this is our general rule for distinguishable balls in distinguishable boxes with some accounting of how many balls go in each box. So n distinguishable balls, let me just abbreviate this, in k distinguishable boxes. So that ni balls go in box I. Well, the number of ways to do this is n factorial divided by n1 factorial, n2 factorial, up to nk factorial. And I don't know if this will come up, but just to, just for your general education, this thing, we were just talking about binomial coefficients. This thing is called a multinomial coefficient. For the reason that if you start expanding something like x plus y plus z, now this is a, trinomial, I guess you might call it. It's a multinomial. These are the kinds of things that will show up in that expansion. So another quick example of distinguishable balls in distinguishable boxes. How many ways to deal a hand of 5 cards to each of 4 players from a 52 card deck. So this one actually has a slightly more straightforward interpretation, although there is a little subtlety. So the balls are the cards. That's a little bit more straightforward. And the boxes are the hands, or let me say, the 4 players. And the rest of the deck. So this is the little subtlety, is that we have to remember to include the 5th hand, which is all the rest of the cards. So to be precise, the boxes are player 1, which has 5 cards, player 2, which has 5 cards, player 3, which has 5 cards, player 4 has 5 cards, and then the rest of the deck has 32 cards. And of course, the balls, there are 52 of them. So according to our general rule, the number of ways to do this is 52 factorial, because that is the number of balls, divided by the numbers that go in each box. So we have 5 balls in box 1, 5 in box 2, 5 in box 3, 5 in box 4, and 32 in the last box. So this is the number of 5 card hands to deal out to each of 4 players from a standard 52 card deck. And just a quick comment, this is a nice application of these kinds of tools. We'll get more into this when we start doing probability later this week. But you can see that if you're interested in card games or dice games or things like this, being able to count how many ways these things can happen could turn out to be quite helpful.